the topic. So I was asked to give a talk about Corcola supernovae and burst sources. So I start preparing the talk, and then I realized that I mean, it's a very wide topic. So I finally decided, I mean, seeing the number of slides that I was having, I decided just to stop in Corcola supernovae and leave the other burst sources for another occasion. There are also two other reasons for that. So one is that the topic of other sources we are thinking in, I don't know, magnetar burst or glitches in neutron stars or fast radio burst and these kind of things. All these kind of sources or those that I just mentioned are probably as complex to model as Corcola supernovae. So if I'm going to fill now more than an hour just talking about this, I mean, one could talk also more than an hour about each of these sources. So these are complicated scenarios in general. That involves a lot of physics. The second reason is that in the case of, for example, magnetars, bursts, or glitches, so they are interesting as sources of gravitational waves because they are very energetic and they are producing very compact objects, neutron stars. So in principle, if a fraction of this energy that is released in electromagnetic waves could be put into gravitational waves, they should be observable. They are also galactic events, so they should be observable. However, all current theoretical models predict that this emission will be very small, so that they will be very inefficient emitting gravitational waves. But on the other hand, as I said, these are very complex scenarios, so we don't really know exactly what is going on. And these are scenarios that one should definitely look for gravitational waves, because if we detect the gravitational waves in one of those cases, that will be I mean, very interesting from the theoretical point of view. On the contrary to these cases, Corcola supernovae is a source that we know that emits strong gravitational waves and that should be detected within our galaxy if one were to happen, which can happen essentially at any time. Okay, so I'm going to focus in Corcola supernovae, not in supernovae in general, but just Corcola supernovae. So this is the outline of my talk. I'm going to divide it in three parts. So the first part, I'm going to talk about the Corcola supernova mechanism itself, just starting from the basics, because I assume that there is some very different background of the people attending the meeting. So I will start just from the beginning, essentially. Then I will address the kind of gravitational waves that are emitted in these cases, and then in the third part, the data analysis tools that one can use to detect these gravitational waves, and the ones that are being developed currently, and that may be the future of the detection of gravitational waves. So let's start with the mechanism itself. Okay, so Corcola supernovae happen in massive stars. Okay, so that's why it's important to start reminding you a bit about stellar evolution. So you start with some star, which is characterized by this, the initial conditions at what is called zero-age main sequence, which is essentially at birth. And is characterized by its mass, rotation, its metallicity, which means its composition, and its binarity. So if it is formed alone or in a binary or in a system with more stars. At birth is essentially hydrogen, and this hydrogen is compressed, and then it burns into helium, and this produces some thermal pressure which supports the star. and then this helium at some point accumulates, and if it reaches sufficiently high temperatures, it will burn into carbon, and then the same will go into oxygen, neon, magnesium, and this will end with iron. Okay, so you are basically burning through this. Can you see my mouse? Okay, you are essentially burning through this network of thermonuclear reaction, in which you are essentially creating iron at the end of the change. The end of the change is iron because it's the one with highest nuclear binding energy, so it's the stable element. Now, that what it produces is that it forms a structure in the star which is formed by shells, and each shell contains a different element, and at the end you end up with a core in the center, which is formed by iron, and this core is not burning anymore because it's stable. Okay, and at this point you may have a corpora supernovae. So the situation is a bit more complicated because it depends on the mass of the progenitor. So here we have the mass at birth, so this Sam's mass, and depending on the mass, different things will happen. So if we have a relatively, if we have, for example, stars with less than 8 solar masses, then the temperature at the center will never be sufficient to ignite the thermonuclear reactions that lead to iron. So those won't produce iron, and they will produce a planetary nebula and end up as white dwarf. So between 8 and 10, they still don't get to produce iron, but they produce oxygen, neon, and magnesium cores. And these cores, even if it is not iron, they can produce some kind of core collapse supernovae. So let's call it, these are called electron capture supernovae, and this is, let's say, some kind of weak core collapse supernovae. Okay, and those produce neutron stars. Now, between 10 and 100 solar masses, all these limits are approximate, and they are actually approximate valid only for solar metallicity. All this depends on solar in many factors, which I will mention later. So I'm talking here about some very standard star, I mean, isolated solar metallicity non-rotating. So those form iron cores, and those will produce core supernovae and a number of phenomena, like not only supernovae, but also annovae or hypernovae or long GRBs. There is a whole phenomenology and different types of supernovae within stellar core collapse. And this can produce neutron stars are black holes. Okay, so if you go out above certain mass threshold, what it happens is that they actually don't produce iron cores. This is wrong here. What it happens is that they are too hot, and then instead of producing a slow combustion, at some point in the evolution, they start producing a lot of pairs, and this pair creation produces an instability which leads to their collapse. It's an early collapse when they are still burning, for example, carbon. And what it happens is that these rapid compressions produce a very rapid combustion of all the material and produces essentially a thermonuclear explosion. So depending on the amount of helium that you had during the evolution, different outcomes can happen. So you may expulse part of the exterior envelope. So these are called pulsating pair instability events, and those eventually will remove the excess of matter and will lead to core collapse supernovae. Or you can have a pair instability supernova, which is, as I said, is a complete thermonuclear combustion of the whole star, which gets completely disrupted and doesn't leave anything behind. Or you can have, if it is very massive, then even if you have a very explosive thermonuclear combustion, the gravity is too strong, and then you produce directly a black hole. Okay, and by the way, this gap that you have here of pair instability supernova is the famous pair instability gap of black holes, which shouldn't be allowed to exist. Okay, in masses in some range, which is not exactly the range of the helium core, but in some range there is a gap which is produced. So for this talk, we are going to focus in stars between 10 and 100. So these are we just call it the massive stars. Okay, those producing iron cores and which will lead to core collapse. So so before collapse, how is the collapse happening? So the core of the star is not supported, the iron core is not supported by thermal pressure because there is no thermonuclear combustion at this point. It's just ashes from the chain reactions. So it's just supported by electron degeneracy pressure. Okay. So this of course, this pressure has a limit, well known. This is the Chandrasekhar limit, which for a non-rotating core object composed by iron, because this depends on the composition, actually depends on the electron fraction. The Chandrasekhar mass is about 1.2 solar masses. Okay, this M should be a solar mass. So the minimum size of the core to produce a supernova is 1.2. Now, if depending on the condition, this core can be very hot or can have a slightly different composition, and this will rise the Chandrasekhar mass in that case, because Chandrasekhar mass raises with temperature. Okay, so in practice, at the times the collapse starts, you have masses with range between about 1.2 and up to 2 solar masses, maybe a bit more in some cases. Okay, but this is the typical range of masses. Okay, its radius is about 3,000 kilometers. Central density 10 to 10 grams in CGS and temperature 10 to the 10 in Kelvin. And one important parameter is the compactness. Compactness is just mass over radius, and here the mass is the enclosed mass at a given number. For example, here in this plot is plot the compactness at 1.5 solar masses. Later I will show other compactness parameters which are relevant. So now, when you go above the Chandrasekhar mass, what happens?
Pablo, there is a question.
Yes, please.
Yes. So on your graph, you have the core mass. What would be the whole mass of the object? So this is only the core, is it? So it's only a fraction of the whole mass of the star.
Yes, this is just a fraction of the mass of the whole star. Actually, I'm going to show later one. So in principle, if there is no mass losses, you can have, for example, I don't know, 50 solar mass star with an iron core of 1.4 or 2 solar masses. Okay, but the thing is that during its evolution, there are mass losses due to winds. So this number can decrease by a lot. So it can be much smaller than the original mass of the star. But yes, this is just the mass of the core, and then there is an envelope which is much larger. In general, is much larger than the core. Yes.
So each part of this graph is an observation. It's an observed object.
No, sure. No, these are not observation. We don't have observation about iron core masses because we don't have access to the interior of the star. So these are all coming from stellar evolution models, and this is one of the big unknowns. Stellar evolution is complicated. I will talk later about this, but it's not observational. This is just coming from stellar evolution models. Yes. Yes, numerical simulations of, yeah. Okay. So once you reach the Chandrasekhar mass, or this mass here that is plotted in this plot, then you start the collapse, and this collapse is accelerated by several processes or two processes. One is electron captures. So the neutrons in the nuclei are capturing electrons, and as you capture electrons, you decrease the electron degeneracy pressure. And the second is the photodisintegration of nuclei, of iron nuclei in particular, which cool the core, so there is no thermal, there is not this additional thermal support, so it accelerates the collapse. So this collapse is relatively fast, so it's about 100 milliseconds, or a few hundred milliseconds. So now you have the iron core, which is collapsing. You have two processes which are happening. First, electron captures, that, as I mentioned, you can see here the basic processes that are going on. And the second is, and related to that, there is neutrino and antineutrino production. So you are at the same time producing, neutronizing the matter, so producing more neutrons. So you increase the fraction of neutron with respect to proton in nuclei and later in free nucleons. And then you are producing a lot of neutrinos. Okay, these two things. So when you reach about, as you compress, you increase the density. When you reach 10 to the 12 gram per cubic centimeter, then neutrinos get trapped because interactions are so strong that the opacities are very high. And then you create a neutrino sphere at this density, and everything inside the neutrinos are just trapped. At 10 to 13, neutrinos get in thermal equilibrium with the matter that are surrounded. And when you reach about 2 times 10 to the 14, then you reach nuclear matter density, and then you get a phase transition from nuclei to free neutrons. So essentially, nuclei disappear, and then you just have free nucleons, which are also mainly neutrons. And this is the seed of what will be the neutron star. Okay, the nuclear forces dominant interaction, not electron pressure degeneracy anymore. So the equation of state stiffens, and this produces a bounce. Okay, so the collapse stops at the center, and it bounces back, while the rest of the iron core is still falling. So you form a shock which is traveling outwards against a flow of iron which is falling towards the shock. Okay. So the situation that you get here is you get first in the interior, you get an iron core, an inner core, sorry, formed by neutrons, which is still cold because the shock was formed at a finite distance. So this material is unshocked. Then you have all this material which has been shocked, so it's very hot, but it's inside the neutrinosphere, so it cannot cool down efficiently. So neutrinos are streaming out very slowly, and when they reach the neutrinosphere, they just go away relatively fast. So this is what is called the proto-neutron star, which is key for everything that I'm going to talk about in the rest of the talk, essentially. And then you have the stall shock, and the shock is stalled. So at some point, it reaches some point of at about 100 kilometers, and it doesn't expand anymore because it's continuously losing energy by dissociating the iron, which is still falling. So the iron falls into the shock, and when it crosses it, you dissociate the nuclei into free nucleons, and all this, all the energy that you need to do this is taken out from the shock. So the shock cannot progress further because it's continuously dissociating nuclei. So it gets stalled at this distance. So this situation stays there for maybe half a second or 1 second. So it's a situation which is semi-stable, and which is interesting. It's the interesting part for gravitational wave emission. Now, during this phase, there is a lot of instabilities and oscillations going on. So I'm going to go a bit over all the kind of things that you can have there, and what are the processes producing these instabilities as oscillations. Okay, so the first thing that you have is buoyancy. You have buoyancy in the proto-neutron star and in the region around, because you have a thermal structure that can produce gravity waves, not gravitational waves. These are just gravity waves. And that this can produce two effects. It can produce convection. So you have convection, for example, when you have a hot material or cold material on top of hot material, and then the hot material will tend to rise. Or if you have dense material on top of less dense material, and these kind of things. Okay. Now, in regions where you don't have this inversion, so you have a stable stratification, like for example in the inner core or the region around the proto-neutron star surface, which I mean is cold on the top because on the outside of the neutrino sphere is cooling very fast, and inside is it cannot cool down, so it is hot. So you have this structure which is stable just at the surface. So in these two regions, you don't have convection, but if you make any perturbation, for example, of the surface of the proto-neutron star, it will oscillate with some gravity waves. Okay, it will produce gravity waves, and in this object, you can have standing waves essentially which produce G modes. These are called G modes. These are just standing gravity waves, for example, in the surface of the proto-neutron star or in the inner core. Now, you can also have pressure waves. Pressure waves are relevant for the production of P modes. Typically, in these objects, what you have are sound waves which are trapped between the proto-neutron star surface and the shock. So they bounce forth and back, and they form here modes, and these modes are called P modes. But also, when you combine those with accretion, you can have an advective acoustic cycle. For example, if you have a perturbation in the shock, this perturbation will be advected down towards the proto-neutron star, and this will produce a perturbation in the surface of the proto-neutron star. And these perturbations produces sound waves which travels back to the shock and produces another perturbation in the shock. So it closes the cycle, this advective acoustic cycle. And now under the right conditions, this cycle is unstable and its amplitude will increase. And this is called the standing shock accretion instability, or SASI. Okay, and I will mention SASI many times later. So it's this instability related to this advective acoustic cycle. Now, if you have rotation, then you can have inertial modes. Inertial modes are modes which are related to, these are modes which are, you can have modes rotating and, co-rotating and counter-rotating with the fluid, and they can be related, for example, to G modes and P modes. So they can be just G modes, for example, in an inertial frame and things like that. And I will show you later some examples of inertial modes that appear in later phases of the, or can appear in later phases of the proto-neutron star. And when you have rotation, you typically also have magnetic field amplification. So you have very high magnetic fields, and this leads to magnetorotational instabilities, which is for rotating objects is a very important instability because it allows very fast or very efficient transport of angular momentum. Okay. So what is the impact of these instabilities in what we are going to talk today? So the first impact that they have is that the matter is not falling, it's not accreting directly across the shock into the proto-neutron star, but it's doing something here in between. So you have some convection, or it's oscillating because of the SASI or something. So this extra time that they have here is time that they are interacting with the neutrinos from the proto-neutron star, and it's time that this matter is getting heated. So the more you heat the material behind the shock, the more chances you have of producing an explosion. The second importance of all these instabilities and modes is that they produce asymmetries in the proto-neutron star, and that will be the main reason for gravitational wave emission. Okay, and we will see later how all these oscillation modes can be seen directly in the gravitational wave emission. So now, as I said, you have a mechanism to deposit energy behind the shock. So if you have a reservoir of about 10 to the 53 ergs in neutrino energy or thermal energy in the proto-neutron star, which is emitted in terms, will be emitted in terms of neutrinos. And if you are able to deposit 1% of this energy behind the shock, then you have a shock expansion, which will disrupt completely the star, will eject all the matter outside the shock, and will produce a core collapse supernova of about 10 to the 51 ergs, which is the typical core collapse supernova explosion. And this mechanism is called the neutrino-driven supernova explosion. Okay, so whenever we talk about neutrino-driven, we are talking about this mechanism. So what is left behind, everything which was behind the shock and that didn't explode, is the proto-neutron star, which is very neutronized and will cool down in some time scale of tens of seconds to produce a neutron star. And this is the source of all neutron stars that we know. So neutron stars are formed during this process. So now, if it happens that you are not able to deposit sufficient energy behind the shock, then what it happens is that the proto-neutron star keeps growing because you keep accreting all the mass that you have outside. So essentially the whole star. So at some point, the proto-neutron star reaches the maximum mass allowed for the particular equation state that you are using, and then it collapses to black hole. And this is the scenario in which black holes are formed. Okay. So what produces black hole formation or supernova production? What produces this? So there are, as I said at the beginning, the initial condition of bells are mass, rotation, metallicity, and binarity, and these four variables create an impact on what is the different kinds of supernova or scenarios that you can have when you have the collapse of an iron core. So regarding mass, so if you look at the lower panel, here you can see in this in the upper part, what you have here is they perform here many simulations, starting with progenitors with masses at birth between about 10 and 120. So the red lines are simulations that produce explosions at neutron star, and this is actually the mass of the neutron star produced, while the black lines are cases where you had a collapse to black hole. So you can see just from here that the situation is very complicated. So it's not just a simple threshold. It's not just, I don't know, about 30 solar masses is black holes and below is neutron star. No, it's a much more complicated situation. And the reason for that is the compactness of the core, which is in the upper panels. Here is this is the compactness at 2.5 solar masses in terms of the solar mass for different progenitors. And you can see that it's non monotonic. So you can increase the mass and suddenly have strong rises in the compactness, and then it lowers up again, and then it has higher compactness again or goes down again. And this parameter is critical for the formation. How compact is the iron core is one of the critical parameters, but not the only, but it's one of the critical parameters to know if a progenitor is going to form a neutron star or a black hole. So and this is very important. It's not so important what is the mass of at birth, but what is the mass and compactness of the iron core at the time of the collapse. So this is really the most important parameter. And making the link between the progenitor and the iron core properties is not so easy because stellar evolution is not easy. Okay, I'm just going to leave it there. So now rotation. I will tell something more about rotation later, but in general, rotation, what it produces is rapid magnetic field amplification, which produces additional source of energy for the explosion. And what it produces is typically magnetorotational explosions, which are very asymmetric, and they are probably linked to events like hypernovae and long GRBs. So all these events are more energetic than typical supernovae by an order of magnitude or so. And they are a class of their own. So these are magnetorotational explosions. So if I talk later about magnetorotational explosions, I'm talking about these kind of things. Now, metallicity. Metallicity is the amount of elements which are not hydrogen in the initial composition of the star. So if you have a low metallicity, what it happens is that the opacities are very small, and then the radiation can stream out of the star easily, and so you don't have any wind, or you have very weak winds, so you don't have mass loss. So here, and this may answer some question before, so this is the initial mass, and this is the mass, the whole mass of the star at the time of the collapse. So you can see that for low metallicity, this is essentially the identity, so it's the same. So a 20 solar mass at the beginning essentially gives you almost 20 solar mass at the onset of the collapse. Now, if you go to solar metallicity, which is the most common environment, especially in our neighborhood, then these additional metals, what it produces is that the opacities are much higher, so the radiation will produce strong winds, and so there will be a strong mass loss. And you can see how strong it can be. So this is especially visible for high masses, and you can see, I don't know, that that for, I don't know, above 40 solar masses, you go down to less than, I mean, slightly about 5 solar masses for the star at the stage in which collapse in which the iron core collapse. Mass loss is also has strong impacts not only in the structure of the supernova progenitor, but also in the rotation. So metallicity is linked, or there are indications that metallicity is linked to things like long GRBs. So some scenarios can only happen if you have, for example, strong rotation and low metallicity, these kind of things. Now, binarity. Binarity is very important, but it's very difficult. So about 70% of massive stars are interacting binaries. It means that they have a closed binary, and they have a Roche lobe which is overflowing, and they have interchange of matter. And this can produce several effects. You can have mass accretion, and you can have envelope stripping. So you can have very strong losses of mass just because the interaction with the companion. In the most extreme cases, you can have these ultra stripped helium cores, where at the end you essentially have the iron core with maybe 1 solar or 2 solar masses on top of it. So they are almost bare iron cores. So, and this is one of the main difficulties of stellar evolution, this binarity issue, because most of the models, actually all of the models that I showed you before, were all computed for isolated stars. So now, what are the uncertainties in the numerical simulations? So I dividing this in 3 parts. So first are the physical unknowns. These are uncertainties that are not solved theoretically in any way. So these are fields of research by their own, and one is the progenitor structure. So it's just the stellar evolution of the star, and with all the uncertainties that I just mentioned, and all the theoretical models and numerical models that are used to evolve a star from its birth to the pre-supernova stage to know I mean, how is the structure at the point in which it collapses to in which the core collapses. Okay. The second big uncertainties equation state of nuclear matter. At high densities, nuclear interactions are well known because this is a very difficult problem. And this is a big source of uncertainty, the equation state. Physical approximations, here I put things that in principle we know how to do it, we know how to solve it, we have done it for simple problems, but the complexity of core collapse supernovae and putting all these things together is so difficult that you end up making physical approximations to things that in principle you should know how to solve. For example, neutrino interaction rates. So you may, if you look at the literature, you may find the authors that use some authors skip some of the reactions just to speed up and these kind of things. Or the neutrino transport is a big source of uncertainties because it's also the most expensive part in numerical simulations. So there are a number of approaches, increasing here, I put them increasing accuracy, so to say. So the more complex it is, the less simulations, the less simulations can you do, the more simple they are. They allow you to make more numerical simulations, so you explore more parameter space. So it depends on what you want to do. You use one or the other. Or the number of neutrino species that you're using, or the gravity treatment. So you are doing simulations with Newtonian gravity or some pseudo-Newtonian potential, or CFC, which is an approximation to general relativity or full general relativity. Okay, so these are numeric physical approximations. And then we have the numerical approximations, which is just, for example, reduction of dimensionality, just doing considering spherical symmetry, 1D simulations, or axisymmetry, just to make things faster. Which kind of grid discretization you're using, which kind of methods you use, finite differences, spectral methods, discontinuous galactic, which kind of methods do you use for the neutrino transport, what is the energy in discretization of the energy of the neutrinos, all these kind of things go into the uncertainties due to the numerical approximation. So I'm not going to go into the details of particular numerical simulations. Okay, I'm just trying to give you a table that helps you kind of interpret what is doing each group, so to say. So, or the things that you have to pay attention. Okay, so when you read a paper and they show numerical simulations from different authors, and you want to compare them, you have to take into consideration that there will be maybe simulations in 2D and simulations in 3D, or there will be simulations which are done with a very simple leakage scheme for the neutrino transport, while others are done with a very sophisticated one. And this produces differences, and the level of accuracy and uncertainties that the waveforms or whatever other observable that you want to get from these simulations will depend on how good are all these approximations treated. Okay. So now rates. So core collapse are rare events compared, for example, to I mean, regarding gravitational waves, they are rare events because they are produced about 2 or 3 per century in our galaxy. So there is a fraction of them which has large uncertainties, but is probably around 15%. That produce they produce black holes directly without any supernova explosion. So we are not seeing these events electromagnetically, but they will produce gravitational waves that we may see them in gravitational waves and in neutrinos. Then about 1% will be fast rotating, and those are the ones which are associated to long GRBs, another type of supernovae, like 1C broadline supernovae. Okay, and that's why the most interesting case is the neutrino-driven explosions, are the neutrino-driven explosions, because these are the most common. Okay, magnetic rotational explosions are rare. Although we know that magnetars are formed at a rate of about 3 to 10%, and if you think that magnetars are formed in cases where you have fast rotation, maybe there is some cases which are fast rotating but are not producing long GRBs, but still producing magnetars, and this is a big unknown right now. So maybe we have the chance that we have some magnet rotational explosions producing magnetars, but at a rate larger than long GRBs, for example. Okay, now I'm going to enter in gravitational waves. Okay, so how are gravitational waves produced? So as I said, during all this process, bounce, all these instabilities going on, the oscillation modes which are excited in the proto-neutron star, all this produces asymmetries in the proto-neutron star, which is the most compact part of the supernova. Okay, this part is the one which is able to emit gravitational waves if you are able to distort it sufficiently. Okay, so if you produce a quadrupolar deformation of the proto-neutron star, then it will emit gravitational waves. So now, from the onset of the collapse, going through the explosion and to the end of the convective phase when the neutron star is finally formed, so you already have a cold neutron star. During all these phases, you can have different kinds of gravitational wave emission. So at bounce, you can have what is called the bounce signal, which I will describe more in a second. Then from the bounce to the onset of the explosion, which lasts at most 1 second, you may have the pass bounce signal, which is characterized by some typical modes. So this is a time frequency diagram, and you will see later that you have very characteristic patterns there related to modes in the proto-neutron star. And in the longer term, the only thing that remains is the signal of proto-neutron star convection. Okay, so after the explosion, you don't have perturbation anymore, but it's still very hot. You have convection inside the proto-neutron star, and this motion will produce some weak gravitational wave signal until it's completely cold and then it starts emitting any gravitational wave. So now let's go one by one. So at bounce, so to have a gravitational wave emission at bounce, you need a quadrupolar existing quadrupolar deformation already when the collapse is when the core is collapsing, and for that the only way is if the core is rotating very fast. Okay, so this bounce signal only happens in fast rotating objects. If you don't have fast rotation, you won't have any bounce signal. And since the majority of the cases are expected to be non-rotating, this bounce signal is expected to be rare. Okay. However, this signal, which lasts only for a few milliseconds, is very interesting because you can relate the amplitude and the frequency of the oscillations that you're getting to properties of the proto-neutron star. In particular, you can relate the amplitude to the rotation rate, exactly because the more rotation you have, the more deformation, and then the amplitude is larger. So in principle, if you can measure the amplitude, then you can put constraints on the rotation rate of the proto-neutron star. And then the frequency is telling you something about the average sound speed inside the proto-neutron star. So if you are able to measure the frequency, which is in this range between 600 to 800 hertz, if you are able to measure that, then you should be able to say something about the sound speed inside the proto-neutron star. Now, convection. Convection is also a source of, or prompt convection is a source of gravitational waves. Prompt convection is observed in some simulation, not in all of them. And it typically appears right after bounce, and it disappears about 50 milliseconds after bounce. So it lasts for a few tens of milliseconds, and then it disappears at a lower frequencies, 100 to 200 hertz. Okay. Now we have proto-neutron star oscillations, which are the most interesting ones. So this is a typical gravitational wave signal from Corcola supernova, and you can see that first is highly stochastic. So it's not a very clear pattern, a sine or a chirp or something like that. It's completely stochastic. But when you plot in the time frequency domain, so you do spectrograms, you can see that it has clear patterns. So you see that the amplitude, the frequency of the emission increases with the time after bounce. Okay, and this is essentially in all the simulations, and this is the result of the evolution of the proto-neutron star, which is accreting material. So, and when it accretes material, it becomes more compact. It's also cooling down, which also helps to become more compact. And it becomes more compact, the typical frequencies of the modes of the star become higher. So what you are seeing here is directly related to the contraction of the proto-neutron star in a time scale of 1 second after bounce. Okay. Yeah, I think so. There are different modes that you can observe here. So this typical feature here is typically associated, which is the strongest, is usually associated to a G mode or an F mode. There is still some debate whether it's an F mode or a G mode. I mean, I particularly think it's an G mode, but I may talk in one of the workshops about this. But let's say that there is some ongoing discussion. But the important thing is that there is a main mode which produces a typical signal increasing with time. Then this signal here, down here, doesn't appear always, only when you have SASI. So this instability that I mentioned with the acoustic advective cycle and the shock. And in these cases, you have this very clear signal of about 100 hertz, which could also be very interesting. So the main interest of G or F modes is that you can relate the frequency, you can get universal relations that relate the frequency of the mode to properties of the proto-neutron star. So if you measure the frequency of the mode at some point, at some time, and you say, okay, here you have at this time, you have 600 hertz, you can go to these relations and say, okay, at 600 hertz, it means that this property of the proto-neutron star is such. Okay, for example, this is a work that we did in which we related we found these universal relations between the frequency and the surface gravity of the proto-neutron star, so mass over radius square. And this includes, it's universal because it's the combination of many different simulations, including different equation states and different progenitor models. And it's universal in the sense that it's valid for any of the models that we tried. So in principle, we can use it always. So this is on the right, you have another example in which, in this case, Otani et al. Related the frequency scale with the mass to the compactness of the star. Here you can see better, better agreement, but they are all, I think they are all for the same progenitor, for example. That's why you don't have so much spread in this direction. But in principle, these kind of relations are very useful because they allow you to do proto-neutron star acceleration seismology. So just measuring the evolution of the frequency in time, you can infer some combination of mass and radius as a function of time. Now, proto-neutron star convection in the long term. So this is a work that we did recently. This is after the explosion. You still have the hot proto-neutron star, which is emitting gravitational waves. So we tried here to estimate the gravitational wave emission under these conditions. So I'm not going to enter a lot into the details, but essentially the main features are that it decreases even if the convection lasts for 10 or 50 seconds. In about 5 seconds, the typical strain amplitude has decreased by several orders of magnitude. So this thing is going to be difficult to detect. It's easier for fast rotating models, so this branch here, actually the amplitude increases with the rotation rate. So this is the angular frequency of the proto-neutron star. I think it is, yeah. And the typical spectrum is for slow rotating cases. So this region here, you have very broad spectrum, which just traces the convective overtone frequency. While if you go to fast rotating cases, what you see is inertial modes, the ones that I mentioned before. And the frequency of these modes scales with the rotational frequency. So these are opportunities that we could use in the future. For example, inertial modes could be used to measure, for example, the rotational frequency, or to say things about the structure of the convective region. Now, for fast rotating, very fast rotating progenitor, you can have what is called bar mode instabilities. It means that whenever the proto-neutron star is rotating too fast, it will try to redistribute angular momentum outwards by producing triaxial instabilities, mainly bars. Okay, it will produce a bar. That is an efficient way of removing angular momentum from the center. This bar, of course, is a very efficient way of emitting gravitational waves, so it's a very interesting source for gravitational waves, only present, however, in cases of fast rotation, which are believed to be less than 1% of all supernova explosions, but nevertheless, it's interesting. And here you have, for example, in the lower panel, some example how a spectrogram will look. You see that it's a very clear frequency because it's just the frequency of the rotating bar, and the frequency is increasing essentially because the object is becoming more compact. Okay. So now the last, I think is the last, yeah. The last thing that I'm going to talk about is memory very quickly. Memory is produced, memory in general, memory, when talking about gravitational waves, memory is the case in which you start with a strain which is 0 and you end up with a strain which is different from 0. Okay, and so somehow the space-time remembers that a supernova explosion, for example, happened. Although this is undetectable because just a constant shift of the strain, if there is no time evolution, this is not a gravitational wave, okay? Because you will need some time variation. It's just a shift in Minkowski, if you want. So this is an example. In the lower panel, for example, you see it very well. So when you have an explosion, you have an asymmetry, which doesn't go back to the original state because the explosion just keeps going on, and this asymmetry is just kept along. I mean, for very long times. We are talking about, I mean, until the matter starts interacting with the surrounding medium. So it may be tens of thousands of years, and that means that you can have that the strength go up and keeps going up and eventually gets a constant state. So this shift from 0 to some value, this transition, this memory, in principle is a source of gravitational waves, a very low frequency source of gravitational wave. We are talking about 1 to 10 hertz. Okay, so this is going to be very difficult to observe with current observatories or even planned observatories. Well, maybe planned observatories will be possible. So now, as a summary, I'm going to put all that we talk about in one single plot. Everything here is approximate, okay? But just to have an idea. So I don't want you to look at the particular things, but just look at the distribution. So if you compare to the typical sensitivity curve, you can see that the different processes emitting gravitational waves are essentially spread all over the sensitivity, the typical sensitivity curve of observatories. So it means that if you ask me which improvement should we make to get best chances of in detecting corpora supernovae, I would say everything. I mean, you need to improve everything. So, or on the other hand, every improvement that you make is a good chance to improve the sensitivity of corpora supernovae in one way or another. Okay. So now I'm going to go just to finally to the last part. I'm going to speak about how we do the data analysis, how we detect these signals, can we detect these signals, or could we detect these signals, and how can we extract physical information from the gravitational wave signals. So now gravitational detecting corpora supernovae is quite different from detecting, for example, binary black hole mergers. And the reason is that template-based searches is not possible, or searches or parameter estimation or anything. It's not possible because we don't have templates that can be used directly to match the observations. And the main reason for that is the stochastic nature of the waveforms. So if you were to run the same model with the same progenitor and all the same physics, and you were to run it 100 times, you will get 100 different gravitational wave signals. They will have common features, like for example, the path in the spectrograms will be almost identical, but the exact strain at each time and the phase, it will be different for each one. So since we just have limited access to the number of simulations that we can do, we cannot simulate anything that can be stochastically produced by nature. So in principle, we cannot use templates directly to compare with whatever nature is giving us. There are other reasons. Also, the complexity and the uncertainties that we have in the modeling are sufficiently high such that the accuracy of the models, I mean, maybe in some cases, especially for example, in the case of fast rotating models, may be difficult, may not be still completely mature to be able to compare, or may have very large uncertainties when you compare models from one groups and others. On the other hand, we have features which are robust. So if you go to the time frequency plane, as I showed you before, you can see here another example. And you have all this feature of G-modes, of SASI, of you may have bar mode instabilities, which are very clear and that they are very robust. And those, in principle, could be used to do parameter estimation because there are non-trivial relations between the progenitor. That could help us to infer the properties of the progenitor star. Okay, the relation with the progenitor is going to be more difficult because, as I said before, the relation between the proto-neutron star that is being formed and the progenitor goes through stellar evolution, and this is a complicated process. And it's not immediate that a signal in particular corresponds to a particular progenitor star. Okay, so if we look at current pipelines, we could classify pipelines in two types. So you can have, or there are two approaches to say. You can try to detect independently waveforms from corpora supernova in different detectors. And then once you have the triggers, the events for each, so I get an event in Hanford, another in Livingston, another in Virgo, and then I try to do an event coincidence analysis, see if these three events, for example, are consistent with a single event. But what is better to do is to use coherent methods. What they do is first they combine the detector data in some way. I will give an example in a second. And then they do a combined data analysis to generate coherent events. So you don't get one event per detector, but you get one event for the network. Okay. The searches that you can do with these pipelines can also be classified in two cases. One is all sky searches. These are searches that you are doing all the time in all the sky. So you are just looking if there is some supernova going on at some point in the sky at any time. And they can be either done in low latency, so just looking in real time continuously, or offline analysis. So, for example, when you finish the observing run, you can process the whole data of the observing run to check if there was something during the run, and then you can do a more comprehensive analysis, for example. The other possibility is targeted searches, which use external triggers, for example, electromagnetic signals or eventually neutrinos, if we detect some neutrino signal. And using this multi-messenger information can help us to say, well, you don't have to look at any point. You just have to look at this small part of the data in time, and then you don't have to look at any point in the sky, but you have to look at this particular point where we observe the supernova, for example. Okay, so this known time, this time window in which you know that the supernova, for example, was going on just from neutrino or electromagnetic observation is known as on-source window. And the smaller the window is, the better the sensibility we have, because what is doing is increasing or decreasing the chances that the detection that you made is just by chance for example, some coincident glitch in 3 detectors. Okay, because there are very smaller chances if you have a smaller window. Actually scales with the size of the window. And these are typically done offline because they are done once you know the trigger. Yeah, and as I said, they need a smaller detection threshold than all sky searches, and that's why they are better if you can do it. Now, of course, this implies that you need some multi-messenger observations. I'm going to hurry up because I only have 10 minutes left, but I think that's okay. So the idea is that you have triggers coming from either supernovae. Supernovae, I'm going to give an example in a second, so I may go faster on this. But essentially, you observe a supernova, and then you try to figure out when it could have, in which stretch of data could have been, and then you observe this stretch of data. Or then you can have a neutrino observation, because at bounce, proto-neutron stars are strong emitters of neutrinos. They could be observed very far away. We are talking about more than 100 kiloparsecs. And there will be alerts, automatic alerts, and within minutes, I think. So we can look at small stretches of data to see if there is something coincident. And of course, you have gravitational waves that we want to combine with the others. For which, for the upcoming, for example, for the coming O4 run, what is expected is that we could detect neutrino-driven explosions up to 10 kiloparsecs and magnetorotational explosions up to 100 kiloparsecs. Now, yeah, just going to comment this. So this is just a list. I just put in here a list of pipelines that are used or have been used in the collaborations to search for core class supernovae. They are, all of them are essentially excess power searches. So they don't assume anything about the source. So they are actually not looking only for supernovae. They are looking for any kind of source which is produced in a which is of the burst kind. It means that is relatively short in time. And in particular, it can detect excess of power related to supernova explosions. And it can be used in both all sky and targeted searches. So the most used one for supernovae is coherent wave burst. Coherent wave burst, for example, was detected the first binary black hole merger was detected, I mean, among other pipelines, it was detected by coherent wave burst, very rapid because it can detect such, I mean, small bursts of gravitational waves. It's a coherent, it's a coherent method, so it uses the whole networks, and it has been used, you can see the reference here, for all sky and targeted searches. So I'm going to skip this and go directly to the targeted search. So here I'm showing, so this is the targeted search that we did for O1 and O2. And what you do is take supernovae within 20 megaparsecs, and you estimate from the electromagnetic, from the time when the first electromagnetic signal was observed, you can trace back using like curve modelings to estimate within a couple of days or a few days what is the onset window. So what is the window of time in which the supernova, the core bounds should have been produced. Okay, because from core bounds to the electromagnetic signal, it is not instantaneous. You have to destroy the whole star, and it can take hours to days. And then the light curves goes up, and the maximum happens at several days after, or weeks after the explosion itself. So there is a big uncertainty from the observed electromagnetic signal to the actual bounds. That is what we want to do. So once you have this, you search within these stretches of data for signals, and in this case there was no detection, of course. And then what you can do is you can inject signals in the same location of the sky and with the same noise, and see how far away we could have detected a signal. And for example, for neutrino driven, we could have detected at a few kiloparsecs. Of course, we didn't detect anything at 6.7 megaparsec. We could have detected magnetorotational explosions at about 10 kiloparsecs. Of course, we didn't detect anything. And we could have detected what is called extreme emission models, which are bar model instabilities, but I mean, taken to the extreme, so to say. So very big bars. So this is to model unknown possibilities, so to say, or extreme possibilities. And in this case, you can see that we can reach, it could have been observed at a few 10 kiloparsecs or about 10 kiloparsecs. That means that if we didn't observe anything, we can put constraints. And in particular, we were able to put upper limits in gravitational wave energy of about, these numbers that are here. So these are, this is the sky search, which has similar results. I'm going to skip this. So now I'm going to enter in the last 5 minutes. I'm going to explain a bit about using machine learning to detect supernova, Corcola supernovae. So this is, I'm not going to explain what is machine learning, because there will be I think 2 tutorials by Antonio Marquina about this. But essentially what you have is a system, an algorithm, which you provide some complex data, for example, an image. So you provide, for example, an spectrogram, and it gives you a simple output. For example, a class. The class can be if it is a Corcola supernova or if it is just noise, in the most simple case. So you can train this network by giving examples with known solutions. So you tell, okay, I give you these pictures of spectrograms that I know are supernovae, and those ones which I know is noise, and then I train the network. And then once it's trained, in principle, it can be used to recognize new images that has never been before, okay, of similar kind. So in the last few years, there has been a lot of work on this. You can see the number of papers just in 2020, using mostly convolutional neural networks. And the key here is what are you using to train the network? So you can use numerical simulations, but numerical simulations, the problem is that there are very few numerical simulations. So just to to be able to train the network effectively, what you have to do is to inject these few signals that you have from numerical simulations in different positions in the sky. So you end up with a lot of injections for the training. So you train with a lot of data, but they correspond only to a few real supernovae. So it's learning something, but maybe it doesn't have the full information. So what we are doing actually, I'm involved in Aston et al. And Lopez et al. We are using phenomenological waveforms. So phenomenological waveforms are not real waveforms. So these are waveforms generated just to look like real, to mimic Korkolav's waveforms. They are parametric in the sense that you can prescribe some, for example, the shape of the curve of the feature in the time frequency domain, but they are at the same time stochastic. So you can create, for the same parameters, you can create multiple realization of the same waveform. So this means that you can train with many you can increase by a lot the number of waveforms, and you can explore very large parameter space. And what we have shown is that training the network with phenomenological waveforms, we can later use this network to detect waveforms from numerical simulations, so to say real waveforms. Okay, and that this is possible. So it seems that this is working in practice. So I'm going to skip this. Yeah. Do I have a couple of minutes, or should I stop now?
No, go ahead. You have a few more minutes.
Okay. So the last part, I have a last part about parameter estimation, which is important. So these are classified more or less the kind of parameter estimations that have been done so far. So the first one will be just blind waveform reconstruction. So, for example, the things that coherent wave burst does is just, just reconstructing the signal is some kind of parameter estimation, because you get the signal, even if it is not telling you anything about the source. You can use, for example, informed reconstruction using, for example, PCA that was done by Heng or by Robert. So you use PCA to decompose a waveform catalog, and then you use this PCA, this principal component analysis, to decompose any new signal and reconstruct the signal. Or you can use also this PCA to classify. For example, this is what is doing SME. What they do is they try to classify signals between magnetorotational explosions and neutrino-driven. Or you can put on top of that, you can put machine learning. But essentially, it's just doing classification in broad categories. The last possibility will be stereosismology, which is direct extraction of the features. This is actually what I'm currently doing. So this is an example of SME, of classification, and you can see here. So this is on here. You are injecting signals which are either magnetorotational or neutrino-driven, and this parameter here is classifying correctly what is magnetorotational and what is neutrino-driven. Okay. And this is an example of stereosismology. On the left, you have the spectrogram, so you can extract the frequency versus time of this particular mode, and then you can use the universal relations that I showed before to compute the evolution of, for example, the surface gravity here as a function of time. And that will be the red curve with the 95% confidence level. And when you put on top of the true value from the simulation, that you can see that it coincides. And in this case, I have to say that the simulation to which it is applied is not included in the simulations that were used to compute the universal relation. So these are two separate sets. So it seems that is working. So essentially here, we are able to recover surface gravity just from the gravitational wave signal. So in principle, it seems that it's possible to do astereosismology. So just to conclude, just the take-home messages first is that core-class supernovae are very complex sources, and this means that if you are working on this, either on the data analysis side or on the modeling side, you should have a strong interaction with each other, because here is very, very relevant to know one about each other. I mean, you need to develop data analysis tools. You need to know about modeling, and if you are doing modeling, I mean, you cannot just put the strain on top of a sensitivity curve and say that to say if this will be observable or not. It's more difficult than that, because there are many things going on. The second thing is that this kind of data analysis is challenging because there is no template matching. We don't have exact templates to match with anything. So we have to be a bit creative when we want to detect these signals, and we should try to explore new ways, for example, of doing parameter estimation. For example, different ways of astereosismology, using different modes, or there are many things to do and to explore, or using machine learning that some people have already started to do, or using multi-measurement approaches, combining data, for example, from neutrinos and gravitational waves to combine parameter estimations of the properties of parameter of the proto-neutron star, and there is already some ideas and some papers going into this direction. And with that, and I'm very sorry for the 5 minutes delay. I thank. So I finish and I thank you.